Have you ever really stopped to think about the device you're watching this on? It feels like magic, but it's not. The incredible power inside our phones and our laptops, well, it's all built on just a handful of truly brilliant foundational ideas. Behind all that magic are 8 great ideas that have totally shaped our world. So let's uncover them. First, let's just try to get a handle on how mind-boggling modern technology really is. Because when you peek under the hood, it is nothing short of a miracle on a chip. Take a look at this. Now, it might look like a satellite photo of some futuristic city, but what you're actually seeing is a computer processor. And inside that tiny little square, we're talking smaller than your thumbnail, are billions, with a B, of microscopic switches called transistors, all working together in perfect harmony. Which, leads to the big question. How on earth do you manage that level of complexity? How do you even begin to design something with billions of moving parts and have any confidence at all that it's actually going to work? Well, the answer, and this might just be the single most important concept in all of computer science and engineering, is the power of abstraction. No, it's a simple idea, but with some pretty profound consequences. Abstraction is really just a fancy word for hiding the messy details. Think about it like driving a car. You don't need to understand how the internal combustion engine works, right? You just need a steering wheel, pedals, a gear stick. All that complexity is abstracted away from you. I love how the computer scientist John Guttag puts it. He thinks of it as this active process. You're deciding what's relevant, and you're deciding what you can safely forget. It's really the art of strategic simplification. So in computer design, this is all done in layers. At the very top, a software programmer just sees what's called the instruction set architecture, or ISA. Think of that as the simple user manual for the car. Then, one layer down, you've got the microarchitecture, which is kind of like the high-level blueprint of the engine. And way, way down at the bottom are the super detailed wiring diagrams. The key is each layer only has to worry about the one directly above it and the one directly below it. That is how you manage billions of parts without going completely insane. So, now that we have our tool for managing all this complexity, let's look at the fundamental building blocks we're actually trying to build. What are the basic parts of pretty much any computer? It doesn't matter if it's a massive server or the smartphone in your hand, they all share these 5 classic components. You've got input devices to get data in, output devices to see the results, and, of course, memory to store everything. But the real heart of the machine, that's the processor. The processor, or the CPU, it really has 2 main jobs. The data path, that's the calculator. It does all the math. And the control, well, that's the traffic cop, directing the flow of information between the data path, the memory, and everything else. And to speed things up, it has its own tiny, super fast little scratch pad right next to it for data it needs in a real hurry. Okay, so we have our building blocks and we have a way to manage their complexity. But how do you combine them smartly? What are the guiding principles, the secret recipe that architects have used to get the incredible performance that we see today? Here they are, the 8 great ideas in computer architecture. We've already talked about using abstraction to handle complexity, but there's also designing for Moore's law, which is basically planning for future tech. And then there's a whole bunch of ideas for boosting performance, like parallelism and pipelining, which are all about doing many things at once. Let's take a closer look at a few of these. So, the most important thing for performance is this: do many things at once. Parallelism is like hiring a whole team of workers to tackle a job instead of just one person. Pipelining is like setting up an assembly line, where each worker does one small step and lots of tasks are in progress at the same time. And prediction is even cleverer. That's about making an educated guess about what the computer needs to do next and then starting the work early. And it's not just about speed. 2 other huge ideas are the memory hierarchy and redundancy. So instead of one giant memory, computers use a pyramid of them, with that small, fast cache at the top and massive, but slower, storage at the bottom. And to make sure things don't break, architects build in dependability through redundancy, basically having spare parts ready to go if something fails, kind of like a spare tire for your car. So what happens when you apply these ideas year after year for decades? Well, you get an unstoppable trend. These ideas aren't just theory. They are the engine of a technological revolution that is almost impossible to wrap your head around. I mean, just soak this in for a moment. On the left, you've got vacuum tubes from the 1950s. the building blocks of the very first computers. On the right, a modern processor. We've gone from these glowing glass tubes to billions of invisible transistors on a tiny sliver of silicon. The physical transformation alone is just staggering. And the numbers behind that transformation? They're even more wild. So if we set the performance per dollar of a vacuum tube back in 1951 as our baseline, just one, then by the time we get to integrated circuits in 75, we're at 900 times better. Fast forward to 1995, and it's 2.4 times million times better. But by 2013, well, the number becomes almost unbelievable. 250 billion. A 250 billion-fold improvement in performance for your money in just over 60 years. That is the result of applying these 8 great ideas relentlessly. It's an exponential curve of progress that's unlike almost anything else in human history. And that unstoppable progress is best shown right here, in this famous chart showing Moore's law. That straight line climbing upwards, that's on what's called a logarithmic scale, which basically means it represents pure exponential growth. It shows how we've jumped from one technology generation to the next, from relays to vacuum tubes to transistors to integrated circuits, all while riding this incredible wave. Think about it. This handful of elegant, powerful ideas built our entire digital world. They took us from machines the size of a room to the supercomputer that you carry around in your pocket. It's an incredible human achievement. Which leaves us with one final and really exciting question. What are the great ideas being discovered right now that will build the world of the next 60 years?